it's something that I've suffered from. And that's how hopefully Alex is still there.
Was that the inspiration for
the original series?
It sure was. I'll send you the link. It was a YouTube video. I'll send you the link.
Send it to me too. The kids will like that.
Alex, you do not have the benefit of seeing the slides either. And that's just the way it's going to be.
Okay.
Unless you can do a quick email.
I have it on a PDF file.
Is it large? I should have thought this.
Is the camera completely out of the question?
No, it isn't. Does do you run Skype on your machine?
But I have internet connection. I'm not here.
I've got Skype.
2 megabytes.
I've never videoed them.
Well, I'm guessing the video the connection's pretty weak here.
2 megs is. He'll be able to email that.
Yeah,
Okay.
It's less than the 5 meg limit.
All right, we're going to take a minute to email that to you.
Okay. I'm not certain I'll be able to look at the PowerPoint and do the Skype at the same time on my device.
That's what I figured. So that's.
That's you want to
Is
try
that an
it?
app thing? Must be pretty close to home.
So lunch is here, meanwhile.
Oh, can't mail that to you.
Yeah, we're talking.
So, what do we got?
sandwiches?
Can't eat all of them.
Sure you can.
It's only like 6 foot long sandwiches.
I'm pretty sure if you try really hard, you can finish it. You are the last user of mail in the entire, like direct user of the mail program on the planet, I think.
Cool.
What do you use?
It's only
Well, something hidden in the bowels of OSX.
I use Thunderbird.
No. He
So Alex
actually
is
used
going
the
to your
mail line.
Gmail account.
Before he opened this. He
Oh,
opened
wow.
Have you never did that one?
Yeah.
The
latest version of Pine?
Sure.
I'm
Well,
trying to switch over the mail
This is a
program
maple
and see what
stuff.
happens.
Okay.
It's not there yet. Give it a minute.
This one is?
Yeah. I don't know what is underneath there, but
This links, what is this?
Links? Yeah.
yeah.
Link rocks.
Can you read it on your phone?
There's definitely time to save.
It makes
Links on your phone.
One of the choices here.
Steve is smart about me.
One of those was meatball. This one is just like veggie.
I thought you were actually going to
Here's the
email
It's been sent.
Damon directly. That's the lost art.
Unless you're going to take them both. No, I've done that.
I'm going to get another napkin too.
As a reminder, you're able to read email and do Skype.
All right, then just listen along as long as you can.
No. I think it's working, so let's...
Okay. Oh, okay. Very good.
It's checking email now. 5 megabytes, you said?
2 megabytes. Tiny.
It might have expanded.
Probably the 2.5 and mine.
I got the email.
No.
Can I recommend meatball and Americano?
And it's a single PDF file called Defense.
Is this beef?
I'm downloading now.
Okay.
You can hear us okay, right?
I can.
That's
Why don't you go ahead and get going? Yes.
All right. So I should start by telling you that my mom called me yesterday and said that her 80-year-old friend's daughter had just reported that when she did her defense, it was the most difficult thing she'd ever done, and that it was more painful than childbirth. So we can hope that she wasn't working in the area of self-modifying circuitry, which is what I've been working on, specifically looking at self-modification, self-configuration as a tool to allow you to efficiently manage extremely large reconfigurable arrays, extremely large meaning on the order of 1 trillion reconfigurable elements, and looking at ways to do this that's very forgiving of defects in the underlying array hardware. And so I've been working on the design and use of a particular reconfigurable architecture that supports this approach. And the work is motivated in part by the idea that somewhere in the next 10 to 15 years, our world might experience a singularity. This would be a technological breakthrough, perhaps, so profound that virtually every graph that you could make that charts human progress hits a discontinuity. So our favorite example, Moore's law, shows this nice steady growth in transistor density going back quite a number of decades and continuing through today. And some people worry that in the future it may actually level off, but it's possible that somewhere down here, 10, 15 years out, it could suddenly skyrocket. And instead of today, where we talk about what to do with a few billion transistors, we might suddenly find ourselves asking, what do we do with 1,000 trillion transistors? How do you organize that many switches to do something useful? How do you handle communication? How do you deal with all the complexities of that many switches? And one way, of course, to do this is to build a large reconfigurable device. And companies like Xilinx have done this for years and made very convincing cases that this is a really good way to organize a large transistor budget. And the reasons, sorry? Oh, blue. The reasons for this are numerous: lower NRE costs, faster time to market, greater flexibility in the field, and if anything, I think those reasons just become more compelling as you scale up several orders of magnitude in your transistor count. That's not a blip.
I think it's network.
Oh, okay. It says your network speed is poor.
Yeah, it's important.
You're hearing yourself.
Okay. I'll stop
Actually,
talking to
hey,
myself.
Alex, can you turn your microphone down or your speakers down? Because they're kind of hot.
So this is the first of 4 hypotheses on which this work is based. The idea that as you continue to scale up your devices...
Can you announce this slide that you're on?
Okay. Hypothesis about future computing. The first point.
This is slide number 3.
Okay.
Do you have examples of singularities in electronics? Previous ones?
Well, the transistor, for one,
Okay.
was a huge one. Development of the integrated circuit.
Although it took a while for its importance to be...
Those took a while, but you can find some funny graphs, particularly from places like the Singularity Institute, where they sort of track the acceleration of how long it takes this development to lead to what you would consider to be significant change. And that time frame, by some measures, is decreasing, and sort of feeds the idea that it's sort of becoming exponential and you're going to hit an asymptote. And that's the idea of this big discontinuity.
So in hindsight, you can see the discontinuities.
Right.
How about in real time?
Hard to say. I mean, contemporary singularities? I'm not sure. It really depends how you sort of define it. And it's somewhat speculative, but it's a possibility, I think. And things like the Large Hadron Collider, I mean, you might suddenly discover a new subatomic particle that lets you do some kind of computation that you hadn't thought of before. With our technology advanced where it is, it seems more plausible today than 20 years ago, 50 years ago, that you might be able to suddenly take advantage of that.
Well, we have quantum computers.
Sure, exactly. Exactly, good example. So hypothesis 1 is just this idea that as you scale up, it makes sense to think about using your transistors to build a reconfigurable device as opposed to custom ASIC. Particularly if you can use a scalable architecture, an architecture where if you can manufacture more transistors tomorrow, you don't need to redesign your device. You can just build more device in some sense. So that's the first hypothesis. Now, as you continue to scale up, Today, a large FPGA might have hundreds of thousands of reconfigurable elements. Something like this might have 1 trillion reconfigurable elements. And what are you going to do with 1 trillion CLBs in your device? And one thing you might do is you might start having multiple circuits running on this completely independently. This could be like a shared, maybe a national resource. And you might have millions of different circuits running experiments from different scientists and engineers. And these circuits could start to become very dynamic in nature. You might have registers that grow or shrink as the data changes. You might take an arithmetic unit and reconfigure it to process text as your input stream changes its characteristics. Or you might have a watchdog circuit that does statistical analysis on the I/O of another circuit, compares to an expected distribution and says, something's a little off here, maybe there's a problem in the hardware. They could pick up that circuit, move its configuration somewhere else, and then start testing those reconfigurable elements to see if a defect is developed. So you can imagine all these complex, sophisticated behaviors taking place millions of places throughout this array, and the question is, how do you manage that? How do you control it? And theoretically, you could take a workstation outside, plug it in through a few pins on your device, and do all of this monitoring and reconfiguration, but that's going to be a bottleneck. So hypothesis 2 simply says, it may be helpful to take that control and management system and move it inside the device itself. Now, if you start trying to design this control and management system, what capabilities do you want it to have? Configuration is no longer something you just do in the beginning and then you run your circuit. It becomes a part of the circuit's operation. So what do you want to do? You want to be able to read configurations, you want to be able to modify them, move them around, monitor inputs and outputs and so on. How do you come up with a design for that? And you can come back to hypothesis 1. Instead of coming up with a fixed design, maybe you should make that control and management system reconfigurable as well. So that's the third hypothesis, is that it may be useful to have the CMS be reconfigurable. Build it out of reconfigurable elements, change it post-manufacture. So now we have a picture that looks like this. We have a base layer of reconfigurable elements. This is, say, 1 trillion elements.
Slide 4.
Slide 4. And you're going to control this with control and management system, so you can think of that as a layer sitting on top of it, and I'm stepping through slides here at each of these layers. So you have this control and management system, CMS, that configures and reads this layer. This is made of reconfigurable elements. How do you control this? You could build custom hardware, but you're going to have some sort of layer, and again, you might want it to be inside the device, because you may have a lot of things happening here. And so you have another control and management system, CMS2. And if that's also made of reconfigurable elements, you have another layer on top of that. And the question is, how far do you build the stack? How far do you want to have layers controlling layers controlling layers? Now, in practice, this may be plenty. You may not need to build 100 layers. You may only need 2 or 3 layers. But there's something else happening here in theory. Basically, below this top layer, below the question marks, all this stuff is software. This is stuff that you can change what it does by loading bits into memories. And above this line where the question marks are, and you decide, okay, this is just stuck in silicon once and for all, that's the hardware. And this question is really, where do you want the line between software and hardware to be? How far do you want to push that up? And where do you say, okay, here's where the hardware is? Hypothesis 4 says maybe you don't. Maybe you find a way to take this top part of the layer and somehow loop it down around and put it under control of the base layer. You close the loop or you collapse the hierarchy. And that's the fourth and main hypothesis of this work, is that if you can have a hierarchy-free arrangement of controlling and controlled objects, that may at least be interesting, probably useful. You can think of this as closing the loop. So hypothesis 4 is the place where all the interesting features of this architecture come from. And instead of jumping into the engineering details of it, I want to take a few slides and just sort of give the motivation for this, tell you where it comes from, because that's really the key to where the whole architecture developed from. Going on to the next slide, hypothesis 4 is basically all about dualism and non-dualism, the idea of subject-object dualism. And dualism is a way of looking at the world in which you see subjects and objects as being different and distinct from one another. So a very simple example, next slide, simple sentence, I kick the ball. There's a subject, that's I, the one doing the action, and there's an object, the ball, that's the receiver of the action, and kick is the verb. Next slide, there's a directionality to this. I'm acting on the ball. The roles of subject and object are very, very distinct from one another. And this is sort of a Western way of thinking about the universe, and it really informs your language, your science, your philosophy, the way you interact with other people, and so on. It's really ingrained in kind of the Western mindset. Nonetheless, after many millennia, Western science made an amazing discovery, which is that when I kick the ball, next slide, the ball also kicks me. When I apply force with my foot to the ball, it applies an equal and opposite force. And so in a very real sense, while I'm the subject acting on the ball, the ball is the subject acting on me as an object. And this is our first hint of a non-dualism, an interaction, an interdependence between subject and object, or between observer and observed. So I want to tie this back into engineering with a specific example. And this example is the one that motivated the design of the reconfigurable elements. So a basic example from computer science, and I'm going up to next slide. Says less philosophical example. Make a program that prints out its own source code. Okay, it's a fun little exercise. And theoretically, it's very easy to do. You have 3 steps. You create an array of strings. You write a program that reads that array and prints out each string. And then you just initialize the array with source code. And when you run this program, it'll go through and it'll print out its own source code. Very easy. So we can do this. We'll go through the next slides. There's the array declaration. This is in C. I'm leaving room for 100 strings. Here's the main program. It has the necessary I equals 0 that every program should have. It loops through 100 times, reads each string, prints it out with a new line at the end. Almost done. All we have to do is initialize the array with the source code. So the first line of the source code is this array declaration, and we can put that into the array. And we put it inside quotes, put a comma at the end. And now we can add the second line of the program, which is this quoted string. So we can put that into the array. We add some backslashes in front of the quotes. And I'm stepping through a few slides here on each step. And then we can add the third line of the program, and that's this new quoted string we just put in. And we can add the fourth line. We're doing really great, right? We're writing a lot of filling in the array here. And the problem is we're moving forward, but we're not getting any closer to the solution. The problem is growing as we continue to code up the solution. And what's going wrong here is that you're taking a dualistic view of the problem. You're looking at the code and the array as being separate. The code and the data, the subject and the object, you're treating them separately. You're saying, here's a copy of the program, that's the object. Here's the program, that's the subject, and we're just going to read this and print it out. If you take that dualistic view, you cannot solve this problem. Because in fact, the code and data are interrelated. When you change the code, you need to make a change in the array, because it's a copy of the code. And when you change the array, that's actually part of the program, so you're changing the program, which will change the array, and you get into this hierarchy again. But you can solve this problem. So here's the first statement of the program. It's an array declaration. And here's the remainder of the program. I'm on a set of C code now on the slide. And this basically does what we just described. It reads the array, it prints it out. The reason this works and the other solution didn't is because we're taking part of the data and we're embedding it in the code. For example, we're saying when you're going to print out a backslash or a quote, we need an escape in the front. And we're coding the fact that you print out the elements twice, once in quotation marks and once bare. And this lets you solve the problem when you honest it prints itself out. And the interesting way to think about this is these last 2 slides, this program, what is it? Is it code or data? And it's code because you can compile it and you can execute it and it will do something. But it's also data because it's the output of a program.
Hello?
Did we lose him?
Is this Alex? Yeah. He says he lost the Skype. Did I? If I interpreted you right.
Does speakerphone work?
Okay, he's... Okay, so Peter is now taking care of you, unless you want to just make the speakerphone.
It's back on. Just the internet, the network in here drops out occasionally.
Occasionally we have network dropouts, but he says it's back now. Are you able to see it? Let me pass the phone over to Peter, because he's working the network.
Alex, anything you want? We can stay on phone. I've got Skype back up. Okay. You want me to just put you on speakerphone? Okay.
Well, then you can be here. Still there?
Yeah.
Awesome. Okay, so this program will print out itself, and in some ways of looking at it, it's both code and data, and that's sort of an extreme case of non-dualism, where subject and object are actually the same thing.
Tell them where you are.
I'll tell on the next slide. So from here, we can talk about the actual engineering details of these reconfigurable elements. So I'm going on to the next slide, which shows a picture of a four-sided single element. And this is the basic reconfigurable element I'm working with. There's different versions. You can have a six-sided, three-dimensional element, but most of it work with a four-sided, two-dimensional one. And each side has two inputs and two outputs. The inputs are labeled B and C. Corresponding outputs, we use north, south, west, east to indicate the sides. And this is a simple input-to-output map. You can load a 128-bit register inside this and tell it how to map inputs to outputs. Now, for a moment, ignore the C inputs. Only pay attention to the outputs and the D inputs. And so you can define the behavior of this next slide as a 128-bit truth table. For each combination of D inputs, you specify 4 C outputs and 4 D outputs. Very simple block, no memory per se, no state in this block. It's just a combinatorial unit. And next slide, you basically take a collection of these elements, you tile them in an array, and that's your reconfigurable device. And in this case, we have a 4x4 set of arrays, a very small array, 16 elements. The inputs and outputs on the elements on the edge are accessible outside the device. All the others are connected internally to neighboring elements. And the way you use this is very simple. You basically just configure the truth tables inside each element to implement logic blocks, pieces of wire, multiplexers, adders, whatever you need to do. And you put them in such a way that they implement some circuit you're after. And it's very straightforward engineering. You can do mapping, place, and route. You can come up with a list of truth tables and load them into the array elements, and you have a circuit. So there's nothing magic or weird you have to do here. It's a pretty straight map from something like Verilog or VHDL into a configuration of this array. And at this point, I'll point out the architecture itself is scalable. This idea that if you have an existing array and you can build more arrays, you can just sort of tack them on the side and make a bigger device. You don't need to come in here and change what's inside the existing array. So next slide, configuring an element. This is the last piece of the question, is how do you change what's in the configuration memory of an element? And this is where you use the C inputs. Basically, if you set a C input to 1, you can use that side's D input to shift in a truth table. And there's a clock that samples the D line, and every time it picks off a bit, it loads it into the next spot in the truth table. And the previous truth table bits get shifted out. So you can use this to read and write the configuration memory of an element if you have access to its C and D inputs on at least one side. And this is called C mode, configuration mode. If all the C inputs are 0, it's D mode or data mode, and that's just a combinatorial block. So next slide is a picture of just 3 simple elements. The middle element is implementing 3 functions. It's putting a 1 to the north on the C output, and it's taking data from the north, sending it back to the north and to the south. What this one element will do with these 3 equations is it will put the element on top into C mode. That element will send its truth table bits out the southern side. The middle element will recirculate them back to the north. So this is non-destructively querying the configuration memory of this element on top. It's also sending a copy of the bits to the south. And this is the beginning of how you build dynamic circuitry. You can actually read and rewrite configuration memories from one element and load them into another. And that's sort of a basic building block. So next slide, it talks about non-edge elements. In a large array, most of the elements are not accessible from outside. Most of them are going to be internal. If you want to configure this element that I've got labeled DC, how do you access that? Because you can't reach its D and C inputs from the outside. But the element to the left of it can. It has direct access to its D and C lines. So what you can do, next slide, is use these 2 elements collectively to control this internal element. So this D line you can route directly into the D input, and the D line below the edge element you can send to the north and route into this target element's C input. And now you can use these 2 elements to toggle the D and C bits of this internal element and thereby control it. And so you go through a sequence of operations. First you configure this element, then you configure the element below it, and then you can configure the internal element. And this is basically how you use the array, by creating sequences. Next slide. A sequence is just a collection of C and D bit values that you send into some circuit to perform configuration operations, such as building a wire, a way to, from some point in the array, get control over the D and C input somewhere to the east, or to build a bent wire to move over and come down, and so on. And collections of sequences are called supersequences, just a terminology. But an example of a typical supersequence would be bootstrapping, trying to load some target circuit into a subarray in this reconfigurable device. So next slide, I'm showing 5 by 5 blocks. And for here, we're going to think of each block not as being a single reconfigurable element, but a collection of elements. It might be several. And suppose you want to bootstrap this. Suppose from the upper left corner, which is on the edge of the device, you want to load certain truth tables into these internal blocks of elements. The way you can go about doing that is you have direct access to the elements in the upper left. You can configure those, and I'm going to step through a series of slides here, kind of a movie. You can configure those blocks in the upper left such that they give you access to the DMC inputs in the second block. You can use that access to configure the second block, and that will give you access to the third block's elements, which you can configure to move you into the fourth block, which you can configure to move you down one row. So now from this point, we have control over this internal element on the first row, fourth column. And from here, we can use this element to configure the first piece of our target circuit. And then we can reconfigure this block again to move control down one spot and use this new element to configure the second block of the target. And you can repeat that to hit the third block and the fourth block. And now we have an entire column of our target circuit configured. And all I had to do with this next slide, full set of sequences, is generate the correct bit sequences. In this case, it was 3 extensions to the east, a turn from the east to the south, 3 pairs of configure and extend to the south, and then a configure to the east. Now you can repeat this set of sequences, but only start with 2 extensions to the east. And what that's going to do is the same thing, but it's going to configure the second column of elements. And you can do that a third time and a fourth time, and there's your bootstrap. So starting just from this upper left corner, you're able to load whatever configurations you want in this internal subarray. And that's a way to bootstrap the system.
You're making assumptions, though, about the reuse, right? That in this architecture, you're assuming that many cells will have identical configurations.
Right.
If you were to, well, it wouldn't make sense, but if you were to load a truly random sequence of bits and configure with a random sequence of bits, then you would not be able to do this.
You can do it with what I'm describing here, you can. What you're talking about will come up in a minute. But there's no reason that what's in here has to be the same as what's in here. You can load whatever configurations you want in there. You're using a particular sequence just to get to each of these spots.
Well, I understand you're navigating first and loading configurations, but as a function of time, if you had a truly random set of configurations, regardless of the order in which you configured blocks, that would still be a very long string.
Absolutely.
And that would limit the time it took to configure.
Oh yeah, this is strict order n. If you want to do 1 trillion blocks, it's going to take you 1 trillion operations.
So it's kind of like Kolmogorov complexity. That looks at a string and asks, what is the shortest program that can generate this string?
Okay.
And so if there's a great deal of repetition, then it can be a very short program.
Right.
But if it's truly random, the length of the program equals the length of the string.
Right, exactly. Right.
So you're relying on a program, basically, to be able to repeat itself and thereby configure entire rows and columns.
Right. Okay, so next slide. What is this useful? Okay, you can bootstrap a subarray with this, but why do you want to do this? Why do you want this non-dualistic approach where you build things that build other things and go back and forth? Why not just use row-column addressability? Or why not just make a big long string of all your configuration bits and shift them through a big scan path and drop them into the configuration memories? Why are we taking this fancy, complicated approach to bootstrapping elements in this array? And the reason turns out to be speed. There's this circuit described in the paper called Medusa circuit, and it has a corresponding Medusa supersequence. And it's basically useful for the case where you're trying to tile your array with subcircuits that are more or less identical to each other. So if you're doing something like a simulation problem where you have the same basic subcircuit repeated throughout your array. This is a very efficient way to configure it. In a Medusa supersequence, it has 4 steps. The first set of steps basically say extend to the east, and if you make any progress, continue extending to the east. So again, looking at our same 5 blocks, and I'm back on the slide with 25 empty squares, you can configure the elements in the upper left corner because you have access to that spot from outside, and you can configure an initial Medusa block. And the way a Medusa block is set up is if you send the right sequence through it, it'll configure a Medusa block next to it. So we can use this first block to configure the second block, and I'm stepping through the slides again here. We can use the second block to configure a third, and then a fourth, and then a fifth. And after this, if we assume that the array ends here at the right edge, any further attempts to configure to the east will fail. So in 5 time steps, we've built 5 Medusa blocks. The next step of the sequence, though, says once you stop making progress to the east, configure to the south, but do it in parallel. And then continue repeating that until you make no more progress. So these blocks are set up so they can operate independently, and now in one more time step, each Medusa block is going to configure a block below it to be a new element, and now we have 10 blocks. And that was 1 time step to build this next row. Another step will build the 3rd row, and the 4th, and the 5th. So 5 time steps got us the first 5 blocks. Total of 9 time steps got us 25 blocks. So this picks up speed as you move through dimensions. And it's a very efficient way to configure a large collection of these subcircuits if you have this similarity between them. It's actually an order square root of n. So if you wanted to configure a trillion blocks like this, it takes you 1,000,000 steps instead of a trillion. And that's a 2-dimensional version. There's a 3-dimensional version where after you have a large sheet of these blocks, you can configure in 1 time step an element above each block on the z=1 plane, and now you're doing an order cubed root of n. So now if you wanted to configure a trillion blocks, it only takes you 10,000 steps. And if you go to an Avogadro scale system where you have a trillion blocks, it takes 100 million steps. So if you do a nanosecond per step, it's a 1/10 of a second to do 10 to the 24th blocks. So that's the key to this, why we're doing all this internal configuration and the non-dualism and such. So you can do these things in parallel, you can distribute them throughout the system. And again, it's all just taking this control and management, moving it inside the device itself, and then taking advantage of that. And Medusa circuitry is a general scheme. You can also do other things in parallel, testing, analysis, and so on. Now, an obvious question if you have a trillion or a trillion elements in the system is you're going to have defects. You're probably not going to manufacture it perfectly. So suppose you have the same thing, 25 blocks, and now on the slide with 3 red squares in it now. Suppose you have these defective areas where, for some reason, you can't use the reconfigurable elements in here. If you run the normal Medusa circuit, you're going to configure your first row, and then when you start configuring to the south, you're going to get shadows under these defective regions, and you're never going to fill those in. So you're going to start wasting your reconfigurable elements that do work just because of ones that don't. So you can make a slight modification to this Medusa circuitry at the end of step 4, next slide. If you make any progress to the south, go back and begin at step 1 again. And now what you're going to see is that as you begin to move down and you get these shadows, you'll fill those in eventually from the side. So on to some movies, which I'm afraid I can't share, but you can still get the techno music. So I have 3 movies here. This is a window into a simulated reconfigurable array. Background color means that the element in that spot has zeros in its truth table. It's uninteresting. A dark green element means that it has some non-zero truth table, but its outputs are all 0. Bright green has at least 1 D output asserted. And red means that a C output is asserted. That element is configuring something nearby. And these 3 red squares, they're places that I've artificially created defects in the simulated array. So that if you try to configure anything inside here, it's not going to succeed. And this little block up here, that's 1 reconfigurable element. So this is about 10 elements by 10 elements. And what we have up here, we have an initial Medusa block that's been built, and it's beginning to build a second Medusa block. And you'll see this sequence of moving over, turning, coming down, and then configuring elements off the side, and then coming out a little less, turning, coming down, and configuring, and filling in the area being configured from right to left. And we'll just run through the basic Medusa sequence where it extends out to the east and so on. So here's what that looks like. So here we're extending to the east 5 steps. And once we've built this first row, all 5 of those blocks will configure to the south in parallel. The defective area obviously doesn't work. We do another extension to the south, and now we're only building 2 blocks because of these defects. But we'll go back to step 1, configure to the east, and we build the second element, fill in that row, and then we'll do another replication cycle to the south. So we're doing 3 blocks in parallel. Each of these steps takes the same time as that initial block build. The simulation slows down because it's a sequential machine I was running it on. So we build this row, and now we start filling into the east. We make progress on that first spot. We'll try to make more progress. And that will fill in the second block. And then we'll see one final parallel configuration to the south where we're building complete rows again.
So how do those know to wait until this row is filled in?
When you build this block, there's actually a flag that gets built into it that indicates, it's called an I am here signal. I need to stop this at the end here. There's this I am here signal, and when you finish generating the sequence to the east, you look for an I am here signal coming back to the upper left corner. If anything has been built, that signal will be asserted, and you generate the same sequence to the east again. If you look for that sequence, if you finish the sequence and you don't see the I am here, then you know you can go on to the south. And after this last one, the I am here from the east and the south comes back empty, so you know that you're done. I don't know why my speakers aren't working. But anyway. Okay, now in that first case, I had artificially introduced these defects into the simulator. Is that available?
Sure.
Okay.
That's a lot of people. I don't think you can do this without technology.
Okay, in that first case, I had artificially introduced defects into the simulator in order to make the configuration deliberately fail. Of course, on a real system, you don't know that ahead of time. That's part of the challenge, is figuring out where are the defective elements and where are the regions that I can use. So what we're going to do is we're going to run another step before we configure a region. We're going to run a scan path. Basically, what you can do is in a region that you're going to configure, you can check to see if the element in the upper left corner is working correctly. You load an inverter into it, you test to see if it inverts. You load ones into it, you see if it puts out ones. You do a series of tests, and once you confirm that that element is working correctly, you use that element to access the element next to it. And you do tests on that element. And once that's working, you move into the next one. And you can move all the way across, and then you can turn at the end, and you can sort of serpentine back and forth throughout this region, testing reconfigurable elements. If you decide that they're all working correctly, you go ahead and you build a Medusa block. If it's not working correctly, if one of the elements fails, we're going to activate what's called a guard wall. There'll be a red line on the edge of the Medusa block, and it basically isolates the defective region from the properly working region. So I'm going to introduce one defective element down here in the simulator. It'll show up as yellow. And we'll see the scan path, followed by the configuration, and then we'll do a parallel operation to the south. We'll scan both regions. This region will find the defect, and it'll put up a guard wall. This will turn into a Medusa block. We'll scan to the east, and again, we'll detect the defect from the east, turn on this guard wall. This is like a 17-second movie, so I have to explain it ahead of time. This may be loud. Okay, not bad. There's the defective region. There's 2 Medusa blocks. We scan to the south. We build to the south, and then we scan to the east. We don't have anything more to configure, and we scan to the south, and there's no elements down here. So what we have is this nice isolation wall, this row of non-configurable elements that prevent anything from here from interacting with anything up here. So we've detected this defective area, and we've isolated it. And now we can build Medusa blocks that avoid it and be guaranteed that unless new defects occur, we're only using elements that work properly. Now you can also do a 3-dimensional version of this. So here's a window into a 3-dimensional array, and this is the z=0 plane. There's no defects here, so we're doing the same thing. We're building an array 5 elements across, 5 elements down. There's our initial row, order 1. Here's our order n, where we're building in parallel 5 elements per row. And after we finish building the sheet of 25 by 25 elements, each element will work in parallel to configure one block above it. And you'll see that right here. And now we're configuring an entire sheet of 25 elements, and it's basically taking the same amount of time as it took to configure one of these elements initially. So that's the order cube root of n operation. Extremely fast. Okay, so super sequences and sequences and being able to generate these and respond to certain conditions, such as the I am here signal. That's the whole key to using the system. If you can do that, you can do all these parallel operations, fault testing, and so on. For the simulations that I did here, I generated all those sequences outside. I used a program, I developed a set of Java classes that let you do basic wire building and such, and invoke those in the proper order inside a Java program. I run it, it generates a file of bit patterns, and then the simulator is able to ingest that and set the ones and zeros properly. What you really want, though, is in vivo circuit generation. You want to be able to generate these sequences from inside the system itself. And it turns out you only need to be able to do a few things. You need to be able to generate a basic sequence of C and D bits. So I'm on the in vivo supersequence generation slide now. You need to be able to generate basic sequences. You need to be able to loop a fixed number of times to repeat a sequence. And you need to be able to do conditional branching, to choose one sequence or another. And you need a way to combine these. And if you can do that, you can generate all the sequences that create the behaviors that I've been talking about. So I designed a series of blocks. This is a basic simple sequence generator block, new slide. This one generates a fixed bit pattern called S1. The bits come out the top, a system clock goes in the bottom, and the whole thing is driven by a go pulse. And the end of sequence is indicated by a pulse on the EOS output. So I designed that and I tested it out and it works fine. It's packaged in a pretty usable form. And these blocks, next slide, can be cascaded together just by putting them together. You can take the end of sequence pulse on S1 and feed the go pulse on S2. And as soon as S1 is generated, it'll start sequence 2 generating. As soon as that's done, it'll generate S3 and then you get an EOS pulse. And you take the bit outputs and you just OR them together. And this whole thing is a super sequence, but it looks like one big long sequence with a go pulse at the beginning and an EOS at the end, and a bunch of bits coming out in between. So then I designed a counter block, very straightforward circuit. It initializes to some value, 3 or 11, when you pulse the load line. When you pulse the clock line, the internal counter drops by 1. And when load or clock are asserted, you get a pulse out either the non-zero or the 0 pulse. And so next slide, repeated sequence. You can put these together and this will generate S1 n times. Basically, you put your start signal into the load. This takes the value of n, which is non-zero. That hits the go line. At the end of S1, the end of sequence drops the count by 1. And as long as it's non-zero, it'll generate another iteration of S1. And when you're done, you get your final end of sequence output. And next slide, you can make combinations of these to basically implement whatever super sequences you want. N2 iterations of S2 followed by S3. That super sequence repeated N23 times with an initial S1 and a final S4. And then you can do conditionals by putting multiplexers into any of these things that feed different Go inputs. And so you can basically just put these things together like Lego blocks or something and build whatever super sequences you need. So next slide, this is an actual layout of some of these sequence generation blocks. In this case, everything on the top where it says timing and above, that's all fixed regardless of your sequences. This is the first sequence I wanted to generate. This is a west to east wire, 4 steps, and this is a counter that moves west to east a certain number of times. When that's finished, you go through this 12-bit sequence, which is a corner. It'll take control from the west and turn it into control to the south. And then we have another 4-step sequence for moving from north to south, and this counter will run it a certain number of times. This is the start of a bootstrap. This moves over, turns, comes down. This is how you would start building a bootstrap circuit, and it runs from inside the system. Completely self-contained, no external intervention necessary. So we have the ability to do parallel configuration. We can do parallel detection, avoidance, and isolation of defects. And we can drive it all from inside the array itself. So the next step is looking at what you actually do with this array as far as getting useful work out of it. And the example I decided to work with was looking at heat flow through mostly a 2-dimensional surface. And so I started with the 3-dimensional heat equation. This is a new slide. 3-dimensional heat equation shows the change in temperature U over time as being this pretty simple combination of second partials of U relative to x, y, z, scaled by this thermal coefficient alpha that shows how easily heat flows through the surface. And next slide, the idea for modeling heat flow is to start with your surface, split it into a set of elements, and make these elements small enough that you can assume the temperature is uniform across each element. So it's something like a finite element approach. And then for each element, you have an initial temperature. You can also set boundary temperatures along the edges where the elements aren't connected to other elements. And now you go through your mesh of elements one by one, and you use that differential equation to find the change in temperature from one time step to the next. You update the temperature of each element, you just keep doing this. And this will give you a way of looking at how the temperature changes in response to the initial conditions and the boundary conditions. So to actually run this in digital circuitry, I took this original surface I'm modeling, I mapped it onto a set of reconfigurable elements, such that each mesh element corresponds to a certain subarray, in our case 64 by 64 elements. And then I implemented a circuit in each of these blocks that would basically evaluate the heat equation to perform a temperature update from one time step to the next. So I discretized the heat equation, basically used the definition of derivative twice, came up with this discrete form of second partial relative to x, same thing for y and z. And then you plug that into the original heat equation, you transform from the xy plane to the column row plane up on the surface mesh. You combine terms, you collect and simplify, and you get this very nice closed form solution that says at column C, row R, the temperature at time t plus 1 is the temperature at t plus this delta. And the delta is just a function of the element's current temperature and the temperature of the four immediately adjacent elements. And the intuition is if the neighboring temperatures are close, your temperature doesn't change by much. If they're very different, temperature will change by a lot. So next slide says heat equation element. This is a block diagram of the circuit I designed to implement this equation at the top. X is an 8-bit master-slave register. It stores the temperature of the element. Signed integer 127 hot minus 128 cold. The temperature is sent through a series of wires to each of the four neighboring elements so that they can perform their updates. And the temperature from each neighbor is read in and sent through the circuit. It runs through a series of sums and difference blocks to basically perform this calculation. There's a multiplication by 4, that's just a left shift 2 bits. And then it's multiplied by alpha. In this case, I assumed a thermal coefficient of 1/8, so I could do a right shift by 3. So you divide by 3, and down here you have your delta. And then on command of a system-wide clock, the current temperature is added to the delta, and the result is loaded back into the master-slave register, and you have the temperature of the next time step. So I converted this into a layout of elements. This is 64 by 64 reconfigurable elements, and it's a pretty direct map from the block diagram to this. Here in the middle is the 8 by 3 set of 8 JK flip-flops to make the temperature register, some blocks, difference block at the top, and then a lot of wire for routing. And the idea was to take this 64 by 64 block, tile it out in an 8 by 8 array to correspond to an 8 by 8 mesh of elements for the original surface, set boundary conditions on the edges, put an initial temperature in each register, and then just step it through time and see how the heat changes. So I took this, I compiled it up into a set of configuration tables, I tiled it out 8 by 8, came up with 250,000 cells, loaded that into a simulator. The simulator understands vectors, so I could treat a collection of bits as being a single number, and using that from the command line interface, I was able to set the edge temperatures how I wanted. I initialized all the internal temperatures to 0, sort of room temperature. And then I could pulse the clock that was shared by all of these, go in and using the vector commands, query the temperature register of each of the 64 elements, and write them down on paper and confirm that the temperature was updating the way that you expected. And so, in fact, this was successfully modeling heat flow according to the heat equation. Now, that was a good verification, but it wasn't very satisfying. It's 250,000 elements with 8 bits each is a lot of data to sort of sort through. So I decided to try to come up with sort of a more interactive way of seeing what was happening. So I took the simulator, I changed it into a server. I took the command line interface and rewired it so that it would read inputs and outputs through a pair of sockets. And then I created a client, and the idea of the client was I would graphically display the mesh that we were modeling, 8 by 8. I would have boundary elements on it, and you could set the temperature of those boundary elements by pointing the mouse at them using the scroll wheel to set the temperature up or down. And all of that would get processed by the controller, turned into a set of commands for the simulator to say set these input values to 1 or 0 to set boundary element temperatures. And then every time the system updated, the controller would send a series of queries asking for the contents of the temperature register in each of the 64 elements. It would get those back, color code them, and send them to the display, red being hot, of course, blue being cold. And so I ran this upstairs on the Mac system that you pointed me to, Cameron, and this is what it looks like. I don't need sound here. So here's the window into the simulated array. This is 512 by 512 elements. Each of these little blocks is one element. And this is the 64 by 64 circuit tiled out. Here's the sheet that we're studying heat flow through. And here I'm pointing to the edge and changing the temperature. So I made one element very hot, one element very cold. Now I'm turning up the temperature as I move up. And you can see the changes being applied on the edge and sort of propagating through. Now a thermal conductivity of 1/8 is pretty small. So a change here obviously doesn't come all the way through. But you can begin to see as I set the temperature in the upper right corner to be hotter and hotter, you can see a little bit of the red sort of bleeding in to the inside of the plate. And so I was just sort of playing around with this. I set the bottom to be very cold. And then in a minute I'm going to go and I'm going to start setting the upper right corner to be very hot. And the surface that I'm modeling will begin to turn red, more bright red towards the edges and fading off to room temperature towards the middle. And this is just a nice sort of interactive way to see whether or not this was actually working, and also to see how much activity was taking place in the individual reconfigurable elements as I ran this test. It's pretty close to interactive speed. If you change things really fast, this sort of gets behind, but you can actually turn off the display. I added a dark option on the simulator. If you turn that off, then this basically runs in real time. So that was a good little confirmation for me that things were actually working the way that I wanted. So next slide, 3D heat flow. I also implemented a 3D version of this, and I don't have a movie for that. The graphics output was sort of underwhelming. I tried some red-blue goggles, but didn't really work very well. But anyway, I did the same thing. I used vector commands. I looked at the numbers and confirmed that the 3D system was also working. The interesting thing here, the 3D system turned out to be 17 by 17 by 5 for each single block. That's about 35% of the number of elements I used in the 2D case. Even though it's using 6 sides instead of 4, more complex arithmetic and wider sums, the reason turned out to be wiring efficiency. 2D version, if you had to go from here to here, you might have to go all the way around the circuit. 3D, you could just jump up, come across, and come down. We know that from PCB design, and that's exactly what I did when I laid this thing out. So what this really pointed out to me was the usefulness of a thin three-dimensional array. Even if you don't make it 1,000 layers in Z, just having a few layers actually helps a lot, especially with automated wiring. So that was kind of a cool outcome for this. And next slide, speed comparison, just to look at some numbers from this. We're looking at 1 trillion elements, heat equation elements, one time step with a 1 gigahertz clock, and I want to look at speed across different versions of trying to implement this simulation. Scalar CPU, very, very slow, 200 minutes, because you have to update each element one at a time. You're doing one thing at a time. So to get to 1 trillion elements, about 3 1/3 hours. Multi-core systems and clusters. Theoretically, if you had 1 trillion cores in your CPU, and if you set up the architecture for accessing memory specifically the right way for this kind of approach, you could get a huge speed up. In practice, what I found was that you were pretty much limited by the depth of the pipeline that you can use for performing an update, because you run into bandwidth contention and you run into memory contention. So the practical speed for a sort of arbitrary cluster type system was about 16 minutes. You cut your 200 minutes down by 12. A reconfigurable or any kind of fully hardware solution can do much better, because each of the updates can happen in parallel, and the interactions are strictly nearest neighbor to nearest neighbor. So depth of the pipeline, 12 nanoseconds for a reconfigurable. Much, much faster.
This looks like it would suit GPU architecture.
Yeah, definitely.
So is that included?
Well,
One of these categories?
it kind of depends how you share memory and communication between them. Again, you could set it up so that it's set up in this sort of von Neumann topology, and in that case, you'd be getting something closer to the reconfigurable speed. But if you have sort of one common network that everyone talks through, or a small set of shared memory that everyone has to access, unless you multi-port it a huge number of ways, you're basically limited by how many things you can do in parallel without having to hit memory more times than your portedness. And so that's where the less impressive speed up comes from.
So the advantage is that you're not partitioning
Right.
over some network.
Right.
Okay.
Configuration speed was also interesting. If you assume 10 to the 15th elements in the 1 gigahertz clock, CPU systems are actually the best. It always takes 2 minutes to boot a PC. Doesn't matter what you're doing with it. You don't, unless you're doing some initialization over 10 to the 15th elements, you're basically just loading the operating system, loading the program, and you're good to go. So that's actually very efficient. An FPGA-based system, or any system where you have one long configuration string that comes in, it's going to take a long time, because if you have 10 to the 15th bits in this element, and you load it in at a 1 gigahertz clock, it's about 278 hours to just pump that string through. On a 2D self-configurable system, if you use this idea of a Medusa circuit where you get this order square root n, that time comes down to 50 minutes, and if you use a 3D system, it comes down to 300 milliseconds. So this again is where you get the advantage of the parallelism and the internal control over the configuration. Defect sensitivity is an interesting comparison. CPUs and such, as we know, tend to be very sensitive to defects. You really want pretty close to perfect manufacture. FPGAs can do a little better. You can do things like the Tarmac project, where you sort of look ahead of time and decide where the defects are in your devices and avoid those. Or EasyPath, where you kind of pair the configuration you're going to load into a particular device. But those sort of need analysis ahead of time, and you're kind of bound by that, and if problems come up during the operation, those don't really address it. With a self-configurable array, you can actually live with defects, and you can find them as you're using the elements. You can do this pre-scan, where you look for defects and then avoid them, put them in a bad element table, whatever, something like an on-the-fly scan disk. Runtime upsets are even more interesting. If you look at an Avogadro scale system, so a trillion elements, and you pick an optimistic failure rate, you're looking at about 3 microseconds mean time between failure. Stuff is going to be failing all the time throughout the system. On a CPU, again, you have very few disposable resources, so these failures are probably going to be noticeable if you're using all of the resources. An FPGA, you can build in redundancy and use tricks like that to deal with a certain number of upsets, but usually redundancy only works until too many things fail. And once too many things fail, the system breaks down. With self-configuration, you can use something called the scrubbing technique, and this is a journal paper that I'm getting ready to send out in the next few weeks. And the idea of scrubbing is you have 3 copies of your circuit, and these are composed of reconfigurable elements with truth tables in them. You can go through and you can look at the truth tables from each of those 3 copies, element by element, bit by bit, vote on them, pick the majority, write it back into all 3 copies. And when you go through this, basically what you do is if there's a single defect somewhere in one of these copies of the circuit, you remove it. So these runtime upsets that would normally become permanent in configuration memories, you can actually cleanse them on the fly. And if you use 6 copies, you don't even need to detect when a defect has occurred. You can take 3 copies, run those, vote on the output, that's your live circuit. These 3 copies you scrub. Get rid of any upsets, make it pristine, switch over and use these 3 copies, vote on the output, that's your live copy, scrub the top 3, you just go back and forth. And again, if you try to do this from outside the system, you have a huge bottleneck, because you might have millions of circuits if you're trying to scrub. From inside, you can do the scrubbing right next to the circuit. And so this lets you maintain essentially perfect operation, as long as you don't have too many upsets in close proximity in time and space. So quick summary, this architecture basically addresses the 4 hypotheses, 1 through 4. It's successful in managing a very large reconfigurable system. I've looked at internal configuration, and it's useful for doing fast bootstrap, as well as defect detection and avoidance and isolation during the bootstrap. You can do parallel testing, parallel configuration, and parallel operation. In vivo implementation is supported using these blocks that I developed. I looked at a sample problem, which was heat flow through the system, and also did a 3D simulation of that, and saw that both cases worked correctly, and discovered the usefulness of having a very thin 3-dimensional array, which you can still manufacture with 2-dimensional technology, but still gives you this benefit of easier wiring. And second to last slide, future work. Simulation obviously needs a lot of work. When you're working with parallel circuits, a sequential simulation is slow. The more parallel, the slower it is. And the really interesting work is with highly parallel systems. So the simulation on a single CPU is problematic. I did some work on spreading this out over multiple nodes. I used a 3x3 array of nodes to do a faster simulation. And it worked, but it wasn't faster because of the communication overhead that overwhelmed the total performance. I'd like to take this and put it on something like System X with 1,000 nodes. And I think the parallelism's benefit would outweigh the penalty of the node-to-node communication. So some work to do there. Also 3D work, coming up with a better way to visualize 3D systems. Design tools can always use more work, smarter place and route. Coming up with a checkbox you put on a circuit that says make this defect tolerant. Also coming up with ways to represent dynamic circuitry and embed that in the tools, graphical ways or procedural language ways to actually capture this idea of picking up a circuit and moving it somewhere else. I've got some initial ideas on how to do that. And then other versions of this basic element, an analog version where your outputs took on continuous values between 0 and 1 instead of just binary values. Tying this element into a mechanical system that could interact with building blocks to physically build a new element, and then using these sequences and supersequences not to just configure elements, but to actually physically create new elements and have this thing be self-assembling. Tying it into a matrix of artificial material and using sequences to control the material properties to create sort of artificial building blocks. And finally, the one I'm really excited about, continuous truth tables, where you have not only continuous values on the inputs and outputs, but essentially an infinite number of rows in your truth table. And this is not only interesting in how you use it, but the implementation details are fascinating. They come into a lot of physics and Heisenberg issues and things like that. So a lot of different future work to work on that I'm interested in continuing this with. A couple of papers that are pretty much ready to go. This first one is a journal paper on the scrubbing technique. The second one's on the scrubbing technique. I need to find a journal for that. Conference paper on this parallel bootstrap system in general that I need to do a few edits on, but that's ready to go. And those will hopefully build on some of these other more recent publications that have come out of this work, as well as some of the earlier writing. So that's all I had to say, and be happy to take any questions, and thank you.
Turn it over to you for questions.
So are there pathological cases for the defects that your mechanism can't recover from?
There are, and it's a good thing, because you wouldn't be able to bootstrap if that weren't possible. Theoretically, you could have a defective part of the array that sort of takes over the whole entire array.
Mm-hmm.
That's how you bootstrap it. Okay, now the chances of that happening are pretty slim, and I actually initially thought that that might be a fairly common failure mode. It's actually very difficult, because the way sequences work, you need to sort of go back and forth between C mode and D mode, and you need to do it just the right way. So your defects, if you sort of throw random bits into a truth table, the current element will fail, and maybe 2 or 3 levels out will fail, but it sort of isolates itself naturally at that point. You have to work pretty hard to actually get it to kind of spread out.
I guess the one that I was thinking about was, what if there are failures in the first column? Right, since you're only propagating south and east.
Right.
You can't, I didn't see a way to go back west.
That's an edge case, definitely. You can do this from the north, you can do it from the east, you can use different sequences to handle these different situations. You would need to do some kind of initial test to make sure that you have access. But you only really need access to, I think, 5 elements anywhere on an edge, 5 consecutive elements, in order to drive this whole thing with the right sequence. One idea is along the edges, that's where you do your really expensive fabrication to make sure the stuff is pristine. And then in here, you do the cheaper stuff where you might have 10% failures or something like that. I think that you can manage it.
So as long as you have something in that column.
Right. And there's a lot of different sequences and super sequences you can use. This is about the simplest one where you go over and come down. You can alternate those, go over one block, come down, go over, come down, and it sort of grows out in a triangle.
Right.
You can go 4 directions if you want, things like that.
So how about varying the supercells as you're building? How much variation can you get?
You can put some variation. So the examples that I was working with the heat equation, each block is exactly the same. You can build in, for example, row column information into each element by looking at its neighboring element's row column and adjusting accordingly. And once you have that, you can start doing differentiation, specialization. It can be very simple, such as every other element is supposed to have some different function, and you just look at the low bit on your column, for example. Or it can be very sophisticated, where you actually store kind of a genome for your entire circuit and do some advanced specialization based on that, build circuits out of a library, and so on. This is really just sort of the beginning of a lot of things you can do with this whole parallel approach.
To what degree does this approach depend on having identical cells?
Base cells, or the cells you're trying to build?
The big cells you're building.
if you're doing this parallel configuration, it's fastest if they're identical. If you're building the same block and you're just tiling it out.
And the opposite extreme, if everyone is dramatically different.
If everyone's dramatically different, you're back to a straight order N. Unless you can find some way in which there's a pattern to how they're changing, that's usually what you try to do. But if it was totally random, yeah, it's strict order N.
Is there some good way to take an arbitrary problem and then map it onto this approach?
There may be. I mean, if you think about procedural systems, CPU memory system, that's a fixed piece of hardware and it can run all these different algorithms on it. So you can start playing between the boundaries of a fully custom ASIC solution and a completely software-based solution. And you might say in the extreme case, you could tile up a series of state machines that were identical, but implemented different parts of your algorithm in software. And that would be very efficient to configure, but then relatively slow in operation. But I think there's some space in between there where you might be able to find a sweet spot. I think trying to automate that would be a fascinating problem to do the analysis on your problem set and figure out where the optimal point is.
And then another question, when I first started looking at pieces, I thought you were going to do a lot more comparison with genetics, biology. Is there a reason you avoided it? Should it be avoided?
I didn't deliberately try to avoid it, and there's definitely a lot of similarities. There's a lot of bio-inspiration behind all of this, primarily in terms of kind of the reasonableness of the idea, perhaps. The fact that the human brain generates 20 watts, and this thing generates more than that. So what's the difference there? Well, the difference, I think, is that you're switching slowly, but you're doing it in a lot of different places, parallelism. And so that sort of helps kind of encourage the idea that you don't need to have the fastest system in the world. If you build a trillion elements and they're running at 5 gigahertz, the thing's going to melt. So you clock it down. Is that reasonable? Can you do something in that? Well, biology would say, sure, absolutely. So there's definitely a lot of tie-ins and a lot of inspiration to come from the natural world.
So you focused on efficiency of configuration, scalability of configuration.
Mm-hmm.
But what about efficiency of communication and I/O, power, energy in general?
Mm-hmm.
Is your architecture able to address that? Like a global clock, for example.
Yeah, to some degree. You can look at how much switching is happening from time step to time step and do some kind of power estimate on that, for example. I haven't looked at that in part because this is all sort of based on this hypothetical technological breakthrough down the road. And so you can imagine what is the switching characteristics going to be of this new transistor. I have no idea.
If cells just talk to neighboring cells, why isn't that an asynchronous interface?
It is asynchronous. There's a clock that's used for configuration, but in terms of mode operation, as soon as an output changes on one element, it immediately drives the input on the next element, and its outputs change as soon as the hardware sort of reprocesses the input. It's not done on a clock. It's pure data flow asynchronous. When I talk about a clock in terms of operating, like updating the state of the temperature elements in the finite element case, that's an artificial clock that I build into the circuit. There's a wire going to all the elements, and I hit a pulse that says update.
Can you shut that clock off when the system's in operation?
Sure. Oh, you mean the configuration clock?
Yes.
No, but that would be nice to be able to do.
Fan out of a trillion is rather extreme.
Definitely.
What
and
kind
it's also a potential.
Skew issues would be rather daunting, even if it's a slow clock.
Yeah, skew issues can be a problem. If you go an Avogadro scale, 10 to the 24th elements, you put it in a 3D box, it's 100 million steps from one side to the other. Not quite as bad.
That would also introduce some asymmetries in layout, right? So
Right.
if you try and distribute a low skew clock, it's not just going to be follow the regular tile pattern.
Right. And Two things for that. One, I've done some work with an asynchronous version of this where the clocks are generated locally. And there's no clocking until you put an element into C mode, and you start supplying the clock with that C input. And that clock is used by the neighboring element to start shifting in the bit patterns. And that, it not only cuts down the amount of clocking that's happening for no reason throughout the system, but it also helps you deal with the skew somewhat, because if you're sending an element from here way over to here on a single system clock, you've got clock skew there. If the clock's generated locally, this element goes into C mode, it starts reading bits out, but it's only when that pulse gets over to here that this element starts clocking. So the clocks actually come out of phase, but they're in sync with their local elements that they're configuring or reading from. The other approach to this is, again, future technology. Imagine a system where instead of sending clocks through a wire, you're sending them from a little burst of laser light, and you have sensors on your elements. That might be one way to distribute a clock that sort of cuts down on the skew and avoids sort of the thermal noise that you get from driving a line up and down.
People have used RF signals.
Yeah.
Broadcasting.
Mm-hmm. Yeah, exactly.
Any more questions? Thank you. Can you step out, please?
Sure.